Okay, so the electric potential is a property of a charge that alters the space around that charge. It's basically a number that tells us how much potential energy we could have at any given point around a charge per column of that charge. It can be a bit confusing. So, one way to help us understand it is to look at ways that we can visualize it, and from that, we'll be able to see ways in which we can use it in conjunction with conservation of energy. So by the end of this video, the goal is to have you be able to use conservation of energy to determine the speed of a charge that moves through a specified potential difference. So here we go. The electric potential exists everywhere in space around a set of source charges. So let's start by trying to understand what the potential looks like for the three source charges shown here. So while we haven't yet found an expression for the electric potential due to these three charges, we can understand the general form of the potential simply by noting that two positive charges repel. We'd have to do work to bring a positive movable charge closer to a fixed positive charge. So the electric potential gets more positive as a positive charge is approached and more negative as you approach a negative charge. From this, we can visualize electric potential three different ways. We have here an elevation graph, a contour map, and a potential graph. So our charges are these three charges right here. We have a positive one at 20 nanocolumns, 8.5 nanocolumns, and a negative 7.5 nanocolumns. Of course, the size of charge is reflected in each of these graphs. The elevation graph, we get a good sense of the electric potential as we get closer to each charge. If I were to bring a charge closer to this positive, to the largest positive charge here, it would take more and more work to move it. Therefore, it would have more and more potential energy. So we can sort of think about the charge as being lifted, like a mass might be lifted up a slope. Similarly, the closer we get to a negative charge, the more potential it would have of being attracted to that negative charge. This leads us to be able to talk about the connection between electric potential and the law of conservation of energy. So let's begin by considering a positively charged particle. The potential energy of our charged particle is determined by the electric potential, as shown in UE equals QV. Now, because energy is conserved, charged particles either speed up or slow down as they move through a region of changing potential. This figure here illustrates this idea. In it, we have a positively charged particle moving from an area of higher potential to lower potential, and over here it's moving from a lower potential to higher potential. Notice that as our positively charged particle moves from a higher potential to a lower potential, it speeds up. And then as it moves from a lower potential to a higher potential, it slows down. As an analogy for this, let's think of like a charge as like a mass, like a rolling ball or something. As a rolling ball moves through an elevation, if the ball moves from a higher elevation to a lower elevation, it's going to speed up. If it moves from a lower elevation to a higher elevation, like going up a ramp, it's going to slow down, right? So that's where the elevation graph really shows how electric potential will affect a positive charge. If it moves from a higher potential to a lower potential, that positive charge is going to speed up. If it moves from a lower potential to a higher potential, it's going to slow down. And we can see from the elevation graph here that when that positive charge is approaching, say, another positive charge, then it's going to slow down. It's moving into an area of higher potential. When it's approaching a negative charge, it's moving from a higher potential into a lower potential. Therefore, it's going to speed up. Unlike a mass, however, charges can be either positive or negative. So we have to keep in mind how electric potential affects a moving negative charge as well. When a negative charge moves from lower potential to higher potential, it's opposite than that of a positive charge. It's going to speed up in that case. When a negative charge moves from higher potential to lower potential, it slows down. You have to make sure that you remember how charges behave depends on the sign of that charge as well. Now, all this moving from higher potential to lower potential business can get cumbersome if we try to keep terming it that way. So we give it a name so that we know what we're talking about. We call it moving through potential difference, which is really just the change in electric potential from one point around a charge to another point. And we give the potential difference the symbol delta V, which really just means we're going to take a final potential electric potential minus an initial electric potential. That's our potential difference. The potential difference between 2 points is also often called the voltage. Now, just to give you a little insight here, when we're discussing potential difference in the context of charges and fields, as we're doing here in Unit 5B, we tend to use the term potential difference. But when we start talking about circuits, which we will in Unit 5C, we tend to use the term voltage. I'm not sure why this is so. We're just going to go with it, okay? Anyway, if a particle at some amount of charge moves through a potential difference, the change in its potential energy, delta U equals QV, where V is our potential difference. Now, because this particle will speed up or slow down as it does this, its velocity is also going to change. So if velocity is changing, that tells us that kinetic energy is changing, right? Therefore, we can use the law of conservation of energy to analyze the motion of the particle. Conservation of energy tells us that my final kinetic energy plus my final electric potential energy will be equal to whatever kinetic energy I started with plus whatever electric potential energy I started with. And if we pull out each expression for our different energies, this is what we end up with. We end up with 1/2 mvf squared plus qvf equals 1/2 mvi squared plus qvi. Now, this is where problem solving can get really kind of confusing. Here, we've got here a v for velocity. We've also got a v for electric potential. Not only that, but the electric potential is measured in volts, for which we use a v to abbreviate. So when doing calculations involving electric potential energy and kinetic energy, I have devised an ingenious way to keep track of which V is which. See, all I do is when I'm writing down the V for electric potential, I just add in a little ticky mark tail onto that V just like this. So I know which V is which. You're more than welcome to use my method, but if you have something else, go ahead and use that. Either way, keeping track of which V is which is incumbent upon you, the problem solver. Anyway, let's take a look at how this stuff works by taking a look at a wonderful example. Here we have a proton with a speed of 2 × 10⁵ meters per second enters a region of space in which source charges have created an electric potential. What is the proton's speed after it moves through a potential difference of 100 volts? What will be the final speed if the proton is replaced by an electron? So in this case, energy is conserved. The electric potential determines the potential energy. Now, this figure here is it's a before and after visual overview of the charged particle moving through this potential difference. Now, a positive charge slows down as it moves into a region of higher potential. So we're going to end up with our proton going slower at the end of this situation. To remember, though, that when we look at the electron, negative charges will speed up. So we should expect to see an answer less than 2 × 10⁵ meters per second for the proton and greater than 2 × 10⁵ meters per second for the electron. So our conservation of energy here can be expressed in this way, where we have our final kinetic energy plus our final electric potential energy is equal to our initial kinetic energy and our initial electric potential energy. Now we're told that our proton here moves through a potential difference of 100 volts. So we can rearrange this to this here, and then we can begin to pull out the expressions for each of those energies, so that our energy conservation becomes this here, where we've got our V for our final velocity and initial velocity, and I've shown you the potential difference, little ticky mark V right there. We plug in our values, we put in our 1.67 times 10 to the negative 27 for the mass of the proton, which you can look up on your table of information, and 1.6 times 10 to the negative 19 as our charge on that proton. And when we run through this calculation, we find that the final velocity of our proton is 1.44 times 10 to the 5 meters per second, which follows what we expected to happen. We expected the proton to slow down as it moved through this potential difference. Now, when we go to look at an electron, we should expect to see it speed up. Now, for this calculation, when we go to put in our mass for an electron, which is 9.11 times 10 to the negative 31, and the charge on an electron is negative. Running through the calculations on this, then, we end up with a final velocity of the electron of 5.93 times 10 to the 6 meters per second, which is greater than its initial velocity, which is what we expected to see happen. So now, just when you thought things couldn't get confusing enough, I'm going to throw in here the electron volt. So the joule is an appropriate sized unit when dealing with macroscopic objects. But when dealing with the atomic or nuclear events, we need a different energy unit. So suppose an electron starts from rest and accelerates through a potential difference of 1 volt. The electron might be accelerating from 0 to 1 volts or from 1,000 volts to 1,001 volts. Regardless of the actual voltages, an electron being negative speeds up when it moves toward a higher potential. So the 1 volt potential difference causes the electron to gain kinetic energy. The unit of energy we use at the atomic level is called the electron volt. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. But with this definition, the kinetic energy gained by the electron in our example is 1 electron volt. In other words, 1 electron volt is the kinetic energy gained by an electron or proton if it accelerates through a potential difference of 1 volt. We'll look at a couple of examples in class. I'll see you then.